Hello friends, this is the first lecture on data communication concepts. In this lecture, we shall discuss the fundamental concepts and basic definitions related to data communication. Let us first have a look at the data communication model. A data communication model will have a source, and a destination. So the communication will take place between the source and destination. The source can be a PC, a personal computer. The destination can be a workstation or a server. Now, the source has to interface with a special device known as transmitter. The transmitter will convert the data to some form which can be sent over some medium. And on the other side, there will be a receiver which will receive the signal from the medium and it will give the signal to the destination. So this is the overall system. So in this particular model, we have PC as a source. The transmitter can be a modem. For example, it can be a modem which converts the signal into suitable form so that it can be sent through some medium. This can be typically a telephone line, and the receiver in this case can also be a modem. This basic model for data communication gives us the different components that you require: the source, apart from source and destination, a transmitter, receiver, and a medium. And these components together, transmitter, receiver, and the medium, can be considered as the communication system. Now, in this communication, let us try to understand what are the basic issues in this data communication. So, what are the key issues in this mode of communication? First of all, it depends on the nature of data, we shall see what are the different types of, what are the different forms of data, in what way they can be represented. Then the second issue in this case is the physical means used to transfer data. We shall see that there exist various possibilities or various types of physical means that can be used, or in other words, we can use different types of medium for data communication. Finally, for efficient communication, you will require processing of data for efficient communication. So these are the three important issues related to data communication. First of all, let us try to understand what do we mean by data, or what is data. Data is an entity which carries or which conveys some meaning. Let us take up an example. Suppose you have a bit sequence like this 1 0 0 0 0 0 1. So this is a sequence of zeros and ones. As it is, it does not really convey any meaning, but when you say this is a ASCII code of a character, it conveys some meaning. That means it is the ASCII code of an English character A, and it conveys a meaning, although this bit sequence individually does not carry any meaning. So this 1000001 is a data which represents an ASCII character known as A. Now we have to send this data over the communication model that we have already discussed. Now to send data, we have to use what is known as signal. That means we have to convert data into some form of signal. Question is, what is signal? Signal is a representation. It is a representation of data in some electronic, electromagnetic, or optical form. That means whenever you will be sending data through a medium, you have to either convert it, transform it into some electronic form or electromagnetic form or optical form. Depending on the medium that you will be using, you have to convert data into one of these forms. So that is your signal. Now another definition which is related to signal is signaling. Signal is nothing but act of propagating data through the medium. So it is act of propagating data through the medium. And for that purpose, you will use another definition or another concept known as transmission. Transmission is nothing but communication of data for propagation and we shall see that this transmission will require different kinds of processing, which we shall discuss in my subsequent lectures. Let us now see, let us consider more on data. The data can be broadly divided into two types. One is analog, another is digital. What is analog data? Analog data is some continuous form, this can be analog data. That means it varies continuously over time. On the other hand, a digital data will have some discrete values. So, over time the digital data will have some discrete values. On the other hand, a analog data will have continuous values. So, this is a representation of some analog data, this is the representation of some digital data. Now, as we have told, as you have seen that the data has to be converted into a signal for transmission over some communication medium. Let us now concentrate on signal. Signal can be represented as a function of time. Or in other words, ST, this represents a signal. And whenever it is represented as a function of time, it is called time domain representation. We shall see what are the different characteristics or parameters involved in time domain representation. There is another form of representation which is in the frequency domain, where the signal is represented as a function of frequency. That time this representation is represented by SF. So, same signal can have either time domain representation or frequency domain representation. We shall see how the same signal can be represented in one of these two domains. First of all, let us consider the time domain concepts, or the way the signal is represented in time domain. Time domain concepts. Now, in the time domain, the signal can have an amplitude or signal strength, you can say, and here obviously x-axis is time. Whenever it has some continuous value over the time limit a, this is a, we say that it is continuous. So, this is a continuous signal over a time limit 0 to a, this is a, and that means it is represented as limit t to tends to a, st is equal to sa for all a. Now, on the other hand, it can be discrete, where it has only finite values. For example, say we are representing with the help of 2 or 3 binary bits. Whenever we represent signal with the help of 3 binary bits, it can have only 8 combinations, 0, 0, 0, 0, 0, 1 to 1, 1, 1. That means it has only 8 discrete values. So in this case it is discrete, so it is not continuous. Depending on whether it is continuous or discrete, we shall see that processing will be different. Now whenever we have a continuous signal, we can define it as periodic. Periodic means the signal is repeating at some regular interval. For example, this is a sinusoidal wave. In this direction it is time, and here the signal strength. Signal strength can be represented by voltage, sometimes by current, some electrical parameter. Here we see this signal is repeating, that means this point has again come here and it is repeated over time. In other words, in this case S t is equal to S t plus capital T, where this capital T is the time period. This is the time period of the signal. So in case of periodic signal, it is repeated over time in this way, and it can be represented by this equation S t is equal to S t plus capital T, and it is from minus infinity to minus infinity to plus infinity. Time varies from minus infinity to plus infinity. Now a periodic signal can be characterized by 3 important parameters or characteristics. What are these 3 parameters? Periodic signal parameters. In other words, whenever there is a periodic signal, it can be characterized by 3 parameters, and these 3 parameters are amplitude, frequency, third is phase. It is represented as A. Whenever it is in volts, the unit can be voltage, volts. Whenever it is a electrical voltage, the frequency can be represented by F, unit is hertz. The phase can be represented by phi, where the unit is degree. Let us consider a periodic signal. This is a periodic signal, a sinusoidal wave, we know that. Now here this is A, say it is 1 volt, 0 to 1 volt, and this is the time period T, and this time period is related to frequency in this way. Frequency F is equal to 1 by T. This time T, it is time. Obviously the unit can be either seconds, milliseconds or microseconds, and sometimes it can be nanoseconds as well. Now in this case the signal is represented by ST is equal to A sine 2 pi F into T. Here F is the frequency, A is the amplitude, and phase in this case is 0, because with at time t it is 0. Let us vary these three parameters of the signal. Suppose we vary the amplitude first. So this is 0.5 volt and this is 1 volt, and period we are keeping same. So here the amplitude maximum voltage is 0.5 volt and frequency is same. In this case time period and frequency is same. Phase is also same as the original signal, but the amplitude is no longer 1 volt, it is 0.5 volt. So the A in this case A is equal to 1 volt, in this case A is equal to 0.5 volt. Now let us vary another parameter. Suppose we vary the phase. If we vary the phase, then say we are starting with the middle of this signal, that means in this way. Here, as you can see, the signal is no longer 0 at time instant 0, and it is having about 90-degree phase difference. That means here phi is 90 degree, and signal is represented as A sine twice pi A, frequency is same, plus phi into t. Now let us vary another parameter, the frequency. Say in this time we have two waveforms. In this case the frequency is doubled here, so the signal can be represented as A sine twice pi 2f into t. So we see this is the original signal, sinusoidal wave with amplitude 1 volt. This is another signal with different amplitude but the same frequency and phase. This is another signal with the same frequency and amplitude, say 0.5 volt as this one but different phase, and this is a signal with different frequency. So in a signal we have seen how these three parameters can be varied, and it can have different representation. Now there is another concept which is known as wavelength, related to the time period or frequency. Say when the signal is propagated in space, it occupies some distance within a time. That means a single wave, how much space it will occupy when it is communicated over some transmission medium in time. That means in time t, what is this distance from this point to the other point, or for this one period. This can be computed by lambda. This is known as lambda wavelength. Lambda is equal to v into t, where v is the velocity of the signal in this particular medium and t is the time period. For example, when the signal is electromagnetic wave which is communicated over space, free space, then the velocity v is 3 into 10 to the power 8 meters per second, and we can substitute it here to get the wavelength for a given time period to compute the wavelength, and we know this much space it will occupy, or distance it will occupy for a complete wave. Now let us concentrate to frequency domain representation. In frequency domain representation of the signal, it can be expressed in terms of different frequency components. For example, let us consider a sinusoidal wave as shown here. This is a sinusoidal wave of frequency f1. And this is another sinusoidal wave with frequency 3f1. If these two are combined, this will form another signal like this, and it can be represented. Suppose the first signal is sine twice pi f1 into t, and we are combining another signal of frequency thrice of this one, f1, but amplitude is 1/3. Here, as you can see, the amplitude here is about 1 volt, and here it is 0.3 volt. So this amplitude is 1/3 of this one, and these two have been combined, and this is being produced. So if you look from a different angle, say, how do you represent this signal? This can be represented as a combination of two sinusoidal waves. In other words, any signal, any complex waveform can be represented as a combination of some fundamental frequencies or sinusoidal frequency components. From this particular figure, we can see that we have a frequency f1 which can be considered as fundamental frequency. The other frequencies, say 3f1, they can be represented as harmonics. We can have other harmonics as well. That means we can have, say, 5f1, 4f1, 6f1, and combine them together. And the period of the signal will be same as the fundamental. But the waveform will be definitely different. It is also periodic. The time period is same as the fundamental, but the appearance of the waveform is different, as you can see. Now, how do you represent this in frequency domain? This is your SF, and here it is F. This is F1, and this is 3F1, let's assume. So the F1 has intensity or amplitude of, say, 1, and the relative amplitude of the harmonic, the third harmonic, is 1/3, so this one. And this is the frequency domain representation of the signal that we have seen. That means this particular signal has the frequency domain representation with two different sinusoidal frequencies, sinusoidal signals of frequency f1 and 3f1. Let us see a related concept known as spectrum. What do we mean by spectrum? When a signal is represented in frequency domain, it will have different frequency components. For example, a square wave like this. This is a square wave. This particular square wave can be represented by St is equal to A into, this is the amplitude, into say k is equal to 1, k is always odd, to infinity, 1 by k into sine twice pi k f1 into t. What does it mean? That means this particular signal can be considered as summation of the fundamental frequency of f1, which will have the amplitude of A because k is equal to 1. It will have the third harmonic with amplitude of 1 by 3 because here k is equal to 3 and frequency 3f1. Fifth harmonic with amplitude of 1 by 5 and frequency of 5f1 and so on. So this square wave comprises of infinite number of different signals. As you can see, it goes from k is equal to 1 to infinity. But in practice, this can be closely approximated by a smaller number of harmonics. For example, let us look at this diagram. This is the square wave. Now, if we take only the fundamental first harmonic and the third harmonic, fifth harmonic, first, third and fifth, then it looks like this. If we take into consideration first harmonic, third harmonic, fifth harmonic and the seventh harmonic, it looks like this. So it is a closer approximation of this rectangular wave. So in this way, we can see that a signal comprising an unlimited number of frequencies can be approximated, and the band of frequencies it comprises is known as its spectrum. So spectrum is the range of frequencies the signal contains. Now, what is bandwidth? It is another very popular term widely used in the context of data communication. In this case, as you can see, this particular signal, which you have shown earlier, not this one, here, this particular signal has the fundamental and the third harmonic, f1 and 3f1. So what is the bandwidth of this signal? Bandwidth is the range of frequency. So in this case, the bandwidth is 2f1. That means bandwidth can be represented as the frequency range over which the energy is contained. Now let us consider a real life situation. We have seen that a rectangular wave can have an infinite number of frequencies. So in other words, it has infinite bandwidth. But in practice, we can neglect most of the harmonics, because their contribution is very small, and we can approximate it by what is known as effective bandwidth. So effective bandwidth is a range of frequencies over which majority of the energy is concentrated. For example, say this is the frequency range 1, say this is 10, this is 100, this is 1000, this is 10 to the power 4, 10 to the power 5, 10 to the power 6, 10 to the power 7, and so on. It is in logarithmic scale, right, and so on. And here we have the say amplitude. Now, for our audio, for our voice, what is the bandwidth or the effective bandwidth of our voice signal? It starts from 300 to about 3400. So this is 1000, 3400. So this is your voice. Bandwidth of voice signal is from 300 to 3400 hertz. If you want to listen good quality music, what is the bandwidth? Bandwidth of a good quality music starts from 15 to 20 kilohertz. This is 10 kilohertz, so it will be somewhere here, 20,000. So this is the bandwidth of music. On the other hand, if we are interested in video signal, what is the effective bandwidth? It is about 4 megahertz, 10 to the power 6, so it is up to this 4. So this gives you some idea about the effective bandwidth of different types of signals, voice, music, and video. Now, whenever you will be sending these type of signals over the transmission medium, is there any restriction? Obviously, the transmission medium, the quality of the transmission medium, as we have told in the beginning, if you remember, the nature of data and physical means used to transfer data. Physical means the transmission medium. The quality of the transmission medium that we are using will play an important role about the quality of the signal that is reaching on the other hand or on the other side of the medium. That means here we are sending a signal through the medium, it is going to the receiver, and obviously this signal and this signal here and here, they will not be exactly identical. It will be decided by the quality of the medium that we are using. That means what is the bandwidth of this medium. Let us see a simple situation. Suppose this is a data that we'd like to send, and this is the corresponding signal, and this is having a bit rate of 2000 bits per second. So 2000 bits per second. And this signal, if it is sent over a transmission medium with bandwidth of 500 Hz, it will get converted into this form at the other end. On the other hand, if it is sent over a transmission medium with a bandwidth of 900 Hz, then it will look like this. This is somewhat better than the previous one. If it is sent over a medium with bandwidth of 1300 Hz, then it will look like this. More harmonics are passing, as you can see. If it is having a bandwidth of 1700 Hz, then more and more harmonics are coming, and it is becoming more thinner. Here it is more wider. That means this signal may not be, we may not be able to detect it as converted back into this and these two ones on the other side, but maybe this one or this one we may be able to reconstruct. And this is the bandwidth in case of 2500. So it is very close to the signal that you have sent from the transmitter end, and this is with bandwidth of 4000. Still it is different from the original one. As you can see, it is quite straight here. Here it is straight, but here you have got the contribution of different harmonics. So later on again we shall discuss about this bandwidth and other aspects when we shall discuss the different transmission medium and their characteristics. To conclude, in this particular lecture, we have discussed a basic model for data communication, the concepts of data, different forms of data, analog and digital and discrete. Then two different representation of signal, time domain representation and frequency domain representation, and what are the parameters involved that we have also seen. And finally we have seen discussed the concept of bandwidth, which is very important while communicating over a medium, because the bandwidth will play an important role, will decide how good will be the signal at the other side. In my next class, we shall discuss the different types of medium that we use in our communication network, in our computer communication network, their characteristics, how they affect the signal, and for efficient transmission, what kind of processing is needed. We shall discuss in our subsequent lectures. Thank you.